Hi there and welcome to this third video on forces GCSE Physics Revision. So today we're going to look at Newton's second law, or mathematical aspects of that, car safety, the difference between mass and weight, and terminal speed. So quite a lot to cover in one session. So let's get going. So Newton's second law is force is proportional to the rate of change of momentum, but with a little bit of mathematical dexterity you can get that to equal force, or become force equals mass times acceleration. So F equals ma. So GCSE, this is a really important equation, can be part of required pracs and things like that. Now, in symbol form, you use capital F there, so not lowercase f, because that's frequency, and then lowercase m and lowercase a. So F equals ma, force equals mass times acceleration. Force is, as ever, measured in newtons, mass in kilograms, and acceleration measured in meters per second squared, which is covered in an earlier video about that unit. Yeah, so it's a really important equation. We will cover momentum later on in a later video, but as I say, this comes from Newton's second law, which is about momentum really, but it can be rearranged or manipulated to be in the form F equals ma2 as well. It's more useful actually, really. I think most physics teachers would agree, saying acceleration is force divided by mass, which is one of the rearrangements. That's a better rearrangement to use really as a starting point really in most experiments. But it's also mass is equal to force divided by acceleration. Now this equation can be rearranged fairly simply compared to some of the other ones. It's just three terms multiplied together or divided. So yeah, it's not too complicated an equation. Now I did allude to required practicals and things like that. So here's one required practical, one practical setup that you can use to investigate this relationship. So you might use masses on pulleys and things like that off the edge of the bench as well, depending on the exam board that you use. The practicals are similar but different depending on the exam board really for this F equals ma section of the course. Let's have a look at using this equation mathematically then. Okay, so if you want to read this question and pause it, then have a little go at it. This is the simplest form of question that you could get on this. So let's go through it then. You don't have to rearrange the equation. It's just F equals m times a. And checking the units there, the mass is in kilograms, which is what we want. The acceleration is in meters per second squared. So it's just multiplying those two numbers. So you get 6,000 newtons. So that's the simplest kind of problem, really. Hopefully that wasn't too bad. What about question 2 now? It's asking you for the acceleration this time. So you could either remember the equation or remember how to rearrange that equation. There's a separate video available on rearranging equations, which is probably the most important thing to achieve good marks in GCSE physics exams, knowing how to rearrange equations. So pause if you want to have a go at this one. So the rearrangement is if you divide by m on both sides, you get a is equal to f divided by m. And you get 200 newtons divided by 4 kilograms, which is 50 meters per second squared. Remember that squared has got nothing to do with the number, so you don't square the 50 or anything. The acceleration is just because there's two s's there really. Okay, so it's s squared. Third question then, this time you've got to calculate the force, and it's a bit more complicated, this one. This one you're going to have to use the equation for acceleration from the earliest video that I did. And just in case you can't remember that or offhand, it's acceleration equals change in velocity over time. Okay, so there's a few steps here. So this is more realistic, like an exam type question. It's got to calculate the force that accelerates a mass of 300 kilograms from rest to 6 meters per second over a time of 3 seconds. So have a little go at that and pause the video if you are. Now the key thing to remember there is from rest means that the initial speed is 0. So they are given a number there really, even though it doesn't look like it. Okay, v is going to be equal to 6, the final velocity, and only given the time that you're going to need to use as well. So there's the equation. Acceleration is change in velocity over time, so v minus u, 6 minus 0, divided by 3, so you get the acceleration is 2 meters per second squared. And now you've got to use the equation that we're looking at now, force equals mass times acceleration. So you've got the mass from the question, and you've just worked out the acceleration, so the overall answer is 600 newtons. So that's a bit more like an exam style question. Now these tables, I don't know if you've seen any of the other videos, but they tend to be fairly straightforward, the first few rows, and then the last row or two a little bit more complicated, looking at units and making sure that everything's in the correct unit. Okay, so if you'd like to have a go at that, pause the video now, and I'll just put the answers up that you can check then. So as you can see there, the last two rows, you've got grams there, where really we need kilograms there, really, okay? And we've got grams in the last one, so that would be 0.1 kilograms, but then you've got the added thing that they want the acceleration in randomly in centimeters per second squared, okay, which is a bit more complicated. Okay, so that was a little bit looking at F equals ma, force equals mass times acceleration. Now we're going to look at forces on cars, okay? So you get the thrust or the driving force or the motive force of a car moves it forward. Then you've got a resistive forces at all times when it's moving. So you will have drag and you'll have friction, for example. So when a vehicle is traveling at a steady speed, the frictional forces balance the driving force. So that's related back to Newton's first law. To slow the car down, the engine force is reduced by releasing the throttle, and the frictional force can be increased by applying the brakes, as we know. Be careful spelling brakes in this section of the course. It's B-R-A-K-E-S, not B-R-E-A-K-S. Okay. Now, this is a section from the highway code here, and we're going to be looking at total stopping distances. This is kind of an equation that you won't find, I don't think, in any of the equation booklets or inside the front cover of exam papers. But it's something you still need to know nonetheless, okay, that the total stopping distance is equal to the thinking distance plus the braking distance. And it's quite clear here. You can see that going faster really increases the stopping distance hugely, okay? So it's a bit of a mixture of units here, but I know a lot of us still think in miles per hour, but going at 30 miles per hour there, the total stopping distance is 22.5 meters, and then going at 70 miles per hour, which is just a little bit more than double that speed, the total stopping distance is a whopping 96 meters, okay? And you can see there the effect on the individual parts by going faster. So the thinking distance is increased by speed, but quite a lot, but nothing like as large as the braking distance. And we'll go in to look at these things in detail, what affects the thinking distance and what affects the braking distance. But first of all, let's just describe what it means. So the thinking distance is the time taken from seeing something, maybe an obstacle or something, to actually putting your hand and reacting, not your hand, putting your foot on the brake. So that's it's to do with reaction time, essentially, okay? And then braking distance will be the distance traveled when you've actually put your foot on the brake and the car is mechanically slowing down, okay? Factors affecting it then: reaction time of the driver will increase the thinking distance, okay? So if you're affected by something like you're tired, distracted, you consumed alcohol or some legal drugs or illegal drugs. Say things like antihistamines sometimes have written on them that you shouldn't, certain ones anyway, they shouldn't operate heavy machinery or drive after you've had them in case it makes you tired, for example, okay? And an increased reaction time will increase that thinking distance. The speed of the car then, as we've already alluded to, will affect both the thinking distance and the braking distance. So that's the only one really that comes up, factor that affects both aspects, okay, the speed. Doubling the speed increases the overall stopping distance by about 4 times, okay. The mass of the car and its contents, that will increase the braking distance. The condition of the road, now I try and be a bit more specific here and talk about, wet, icy, slippery roads. They will cause the braking distance to increase. The condition of the vehicle then is more to do with braking distance as well. So worn brakes, worn tyres. Don't just say brakes or tyres in an answer. You have to describe that they're not in a great condition, so they're worn. They will both increase the braking distance. So it's important that you make sure your brakes are in good condition and your tyres have got a lot of tread on them. And that's the end of that section really on car safety. We will come back and look at that a little bit more once we've covered momentum, which will be in a future video. So mass and weight then. In our everyday lives, a lot of people use these terms interchangeably, including myself. But in physics, there is a specific, they are different, okay, essentially. So mass is the amount of matter in an object. It's not a perfect definition. It's not that easy to characterize, really, but that's as good as any I've seen, okay? The amount of matter in an object is its mass, and it's measured in kilograms. the mass of an object would be the same no matter where you are. So on the moon or on the Earth, you'd still have the same mass. Whereas weight is the force of gravity on an object, and it's measured in newtons, as I mentioned in previous videos. And the weight of an object on the moon, for example, would be about 1/6 of that on the Earth. Okay, so if you suddenly clicked your fingers and you ended up on the moon, then your weight would reduce, but your mass would stay the same. One other point here about how you measure these things. A Newton meter you'd use to measure the weight, in this case of a parcel. Mass is measured then using a mass balance. And I think you need to be careful when you write exam answers to do with measuring masses. I'd always use the term mass balance. I wouldn't use the term scales, because quite often in mark schemes they say that that's not allowed. Okay, so I'd avoid use of that language, and because we want to make sure when we've answered a question that we've got the answer right, what the examiner wants. So yeah, always stick to mass balance or electronic balance or something like that for measuring the mass, and Newton meter hopefully for measuring the weight. Okay. Now I've got a little section here about inertia, which is a word that's in some exam boards. Inertia is defined as the resistance of any object to its change in its state of motion or rest. Okay, so large mass objects have got lots of inertia. So there's an example here talking about the enormous mass of a space rocket system means that the thrust force required by the engines has to be huge. The mass of an object dictates how easy it is or difficult for the object to move, and that's called its inertia. Okay. And there's a little bit of a recap there of Newton's first law. Now, there's a really good video by Kurzgesagt, I'm not sure if that's how you pronounce it, about escape velocity, which is really worth watching to really understand how complicated it is to get objects into space. So yeah, if you type in Kurzgesagt on YouTube and the escape velocity video, then it's really worth watching. Now, the acceleration due to gravity, little g, varies from planet to whether you're on a planet or moon, star, or different planets, different stars, different moons. And it depends also on the height of an object. Okay, some examples on the surface, I guess, of these planets would be, we say it's 10 on Earth in some courses. Some other courses will be 9.8, so just check with your exam board there. Okay, as you can see, the moon has got 6 times less value. Okay, Mars is quite a lot less than the Earth. Now, often when I ask students about Jupiter, what they guess Jupiter would be, and sometimes they guess that it's really big, like 1,000 or something, but it's 24, which is more than double Earth's acceleration due to gravity, but it's because it's not as big as some people might imagine, because Jupiter is mostly made of gas. Okay, it's got a rocky core, they believe, of unknown size, but it's mostly made of gas. It's a gas giant. Pluto, on the other hand, has got a tiny acceleration due to gravity, and the unit for this is, it's an acceleration, so meters per second squared. And the Sun, 270, which again, people often underestimate because it's not a solid object. Okay. Now, the gravitational field strength is a term that's very similar. Okay, it's an alternative way of measuring the strength of gravity, and it's defined as the force exerted per kilogram. And near the Earth's surface is also equal to 10 or 9.8. But look at the unit now. The unit is different. Okay, it's the force per kilogram, so newtons per kilogram. Gravitational field strength in nearly all cases is numerically equal to acceleration due to gravity. But you can see the units are different there. Okay, and they're both given the same symbol G. Now let's have a look at the units just for the sake of it. Okay, so newtons per kilogram doesn't look the same as meters per second squared, but it is. Okay, if you have a little look at the bit in brackets, Newton, the equivalent to a Newton, if you look at F equals ma, newtons equals kilograms meters per second squared. So for the gravitational field strength, we'd have, instead of Newton per kilogram, we could have kilogram meters per second squared per kilogram. And the kilogram terms cancel, and so it leaves meters per second squared. So hopefully that hasn't confused you, but hopefully that's shown that the units are equivalent, essentially. Okay. But I wouldn't worry about it, too much. But it's good to know the difference, or not the difference, the similarity in the units, or the equivalence of the units. Right. What about calculating weight? Now, this equation might look new to people, or hopefully you're looking at this as revision, though. But it is essentially just F equals ma. Weight equals mass times acceleration due to gravity. W equals mg, F equals ma, where W is a force, okay? And G is the acceleration due to gravity, a specific type of acceleration. So it's not really a new equation, is what I like to tell students. Weight is measured in newtons, mass in kilograms, and the acceleration due to gravity in meters per second squared. And on Earth, on the Earth's surface, a mass of 1 kilogram has an approximate weight of either 10 newtons or 9.8 newtons, depending on the course that you're doing. Now we're going to move on to falling objects, which is the final section. Okay, so terminal speed or terminal velocity, often this is called. Okay, so when an object falls through air or some other fluid, initially the only significant force acting on it is the downward pull of gravity, although we say weight. Okay, so I wouldn't use the term gravity or anything like that. I'd say weight is the force acting downwards. Okay, and there's an object there accelerating down at 10 meters per second squared. And you can see the weight is shown there. And usually I put that arrow touching the bottom of the object myself. As the object speeds up, frictional forces such as air resistance become greater, and the faster the object moves. Eventually, the resultant force on the object will be zero when the frictional forces equal the weight of the object. Now, this just seems like a lot of text, so I'm going to show you a little animation, hopefully later, that will explain this a little bit more clearly. The object then moves at a constant speed called terminal velocity. Now, leading up to this point, really, we're talking nearly all the exam questions, really, over the years, they ask you to describe this scenario about in terms of forces, okay? So describing what happens. Often it could be a skydiver or something like that, jumping out of a plane. What happens? Describe what happens in terms of changing forces and forces staying the same, okay? But terminal velocity or terminal speed is a constant speed, okay? As I mentioned here, this is an exam tip. Lots of exam questions. They use an object falling in water, and that can throw students. When I first started teaching, I used to talk about air resistance all the time. But then, what if something's falling through a liquid like water? They don't often accept things like water resistance. So I found over the years that it's better to use the word drag. Okay, drag covers both air and gas, water, liquid cases. Okay, so any fluid you could say drag. Okay, as the force acting upwards. Okay, so that is a catch-all term. Okay, so drag going up, and then you've got weight acting downwards. Okay, and another useful tip, hopefully, to remember is that in general, you can have a very obscure question with a complicated scenario, but the weight never changes. Okay, only the drag force. So in that little picture you've got there, the weight's acting down, drag force acting upwards. Okay. And it's really important, to not say about the weight changing, okay? Because you can shoot yourself in the foot in exam questions there, okay? Now here we've got a limited in terms of usefulness graph here. Just trying to show you that you can see a terminal speed there of the object when it was falling through the liquid of about 1 meters per second. I don't find it that helpful, this particular picture, because it looks like there isn't a terminal speed for that object in the air, but eventually it will curve that line and go horizontal at a higher speed. Okay, so let's not pay too much attention to that slide. So as I said, often you get questions about parachutes. I'll put the full slide up here. So a parachutist will have two different terminal speeds. Before opening the parachute, when weight balances the drag force, you'll have a terminal speed of around 60 meters per second. Afterwards, due to much greater drag force, the terminal speed will reduce markedly to maybe 4, 5, 6 meters per second there before the parachutist lands. Okay, let's have a look at the graph here. So I'll put the full thing up. I think probably pressed too many buttons. There we go. So this is the type of graph you have, a velocity or speed time graph. So initially you've got acceleration, so you've got a diagonal straight line going up initially, where when the skydiver jumps out of the plane, the only force acting on them is their weight acting downwards. Okay, and as they fall down, they accelerate, but as they accelerate, they push more molecules of air out the way, and that starts increasing the drag. Okay, and so that's where you get this straightening of the line then. So eventually becomes horizontal as the drag increases to be equal to the weight. So I'm talking about this bit here at the top. So where it's flat, that's the first terminal velocity or terminal speed. So at that point, just to reiterate, the drag equals the weight. And then the parachute is opened, and then you get quite a drastic change then, okay? You get a sudden deceleration, and initially the air resistance is huge, or the drag as you open the parachute, in this case in the air. The drag increases enormously over a very short period of time, and deceleration occurs the weight, remember, stays the same, but as deceleration is occurring, the air resistance becomes less, and then eventually you get a bottoming out or flattening out to get a second terminal speed there. Okay, so here I've got an animation, an old animation, which is really good, I think, at showing this. So initially, look, we've got initially was just weight acting when the skydiver jumped out of the plane, and as time goes on, the air resistance increases. Okay, and then you can see then that the weight doesn't change, and eventually the air resistance or the drag will be equal to the weight, and that is your terminal speed. So it's quite nicely shown, I think, this. And then a little bit of time later, the parachute is opened, and look what happens there. The air resistance or drag is huge. The weight doesn't change again, remember, but then the air resistance does reduce in size, okay, to be equal to the weight. So pretty soon, pretty quickly, then you get a second terminal speed, okay? So I quite like that little animation for showing this. And as I said, most exam questions you get marks for talking about the forces, not for saying speeds up, slows down, that kind of thing, but talking about the interplay of the forces and what the resultant force is. When there's terminal speed, there's no resultant force, and talking about balancing, okay, of the weight and the drag force. Right, I hope you enjoyed that video. Please, if you did enjoy it, please like and subscribe, and watch some of the other GCSE revision videos as I put them on. Take care.